Welcome to today's presentation, Advances in Developing Design Storms. I'm David Curtis, a Senior Vice President at West Consultants, and I've been working on design storm concepts for the last 20 to 25 years. Now, design storms have been around a long time. Now, just because they're old doesn't mean they're bad. Sir Isaac Newton in the late 1600s published books on mathematics and engineering mechanics whose concepts are every bit as valid today as they were back in the 1600s. However, many of the design storm procedures that are in widespread use today were developed at a time where we had far less data, far less resolution data, fewer tools to actually analyze the data, and assumptions were made that may not necessarily hold up in today's world. In addition, over the last 20 or so years, we've had just a rapid advancement in technologies. There have been better tools to analyze large data sets. More and more data observation networks are being deployed, and different types of observation networks are becoming a critical component of our data analysis. In our hydrologic applications, the idea is to develop some sort of design flow at an appropriate risk level that our designed water infrastructure can manage successfully. You typically do that by using a design storm, input that information into some representation of a watershed, and out pops a design peak discharge or a complete hydrograph. The design storm includes specific parameters. We have to understand how much rain actually fell, how it was distributed over space, and how it was distributed in time. Now, we measure rainfall typically with a rain gauge. Now, an important thing to remember with rain gauges is that they only measure rainfall over a very, very small piece of real estate. Even if you have a relatively dense rain gauge network of, say, 1 every 10 square miles, you're still measuring parts per close to a billion in terms of representing water over a large area or representing the rainfall over a large area. So it's always something that we have to keep in mind in how we develop our procedures. To develop a design rainfall depth, the National Weather Service collects rain gauge data from around the country, thinks about it a long time, makes sure that the quality is correct, and then they put it through a fancy statistical analyzer, and they develop an interactive website called NOAA Atlas 14. This website provides us information about point frequency estimates for precipitation. All I have to do is point my cursor at a location in central Texas, and out pops a table of all of the information I would probably need to determine rainfall amounts for a given duration and a given frequency. For example, if I'm interested in a 25-year event lasting about an hour, then my rainfall for that event is 2.7 inches of rain. The NOAA 14 tables also include some additional information, which is the range of uncertainty around that number. So what that actually means is that there's a 90% chance that 2.7 or the actual 25-year event, I should say, for 60 minutes lies someplace between 1.96 and 3.67. The reason that there's a wide range there is that our data records aren't long enough to shrink that range of uncertainty down to more manageable levels. As we gain more data, this range will decrease over time. But it gives you a range of how confident you can be about that number. Now, once we have our rainfall depth, we have to associate it with an area. Otherwise, we can't get the volumetric estimate of how much water is entering a particular watershed. Now, there are a number of ways to handle that. Rainfall is highly variable in Texas as it is in other parts of the country. But let's make a simplifying assumption for the sake of time, and we're going to call it a uniform distribution. And in this particular case, we're going to assign the same rainfall amount everywhere in the watershed uniformly. But now I've created a problem. I have a point estimate of a given duration and a frequency, but now I'm applying it as an average over an area. Are those two numbers the same? The shorter answer is no, they're not. The aerial estimate on an average is always less than the point peak. So the idea then is to create or take your point estimate of a given duration and frequency and derive the aerial estimate for the same duration and the same frequency. We do that with a factor called the depth area reduction factor. So if I have a rainfall estimate for my 24-hour storm, 10-year frequency, I multiply it by a depth area reduction factor, and that yields an aerial estimate at the same duration and the same frequency. Now, where did this depth area reduction factor come from? Well, that's one of those things that was developed a long, long time ago. In this case, the work that was done in the first half of the 20th century, and at the top you see TP29, it's actually Technical Paper 29. There was a series of them published in the late 1950s by what was then known as the U.S. Weather Bureau, but now we all know it as the National Weather Service. This simple chart relates the area in square miles of your watershed with the amount of reduction that you want to apply to the rainfall amount at a point. And the chart basically covers rainfall durations from 30 minutes all the way up to 24 hours, and with watershed sizes up to about 400 square miles. So if I have a 100 square mile watershed, I just use this handy dandy chart, go up to my 24-hour curve, and I go over and see that my reduction factor is 0.93. So I multiply my point estimate by 0.93. That gives me the aerial estimate for the same duration and frequency. Now, a little bit of background. There wasn't a lot of data around to actually do a great job of developing these curves, yet these curves are used all over the world. If you can look here, there are 7 what they determined was dense networks, ranging from 90 square miles to 400 square miles, I think is the biggest one. But look at the length of record. Average length of record was about 12 years. So that's not much data at all to make these kinds of estimates that impact so much of our designed water infrastructure. Once we have our depth established for the watershed, we want to look at the temporal distribution. So there are a number of ways that that can be done. Here's an example, and it's called a nested design storm. And by a nested design storm, it's basically this shape, but if you look at the maximum rainfall for any period from 15 minutes, 30 minutes, hour, all the way up to 24 hours, the rainfall contained in that duration is always equal to the 10-year event for that duration. The shape that you see here is a very common shape among design storms, particularly in urban areas, because it sort of combines the features of an intense thunderstorm in the center of the event and volume for say a 24-hour period. The peak intensities, the really intense stuff, would be important for inlet design structure or conduits or pipes for an urban drainage system, and the 24-hour volume would be appropriate for designing a detention pond, for example. But in this one curve, they kind of combine the features that address both design problems, and it's commonly used. But in the intervening years, there have been just an influx of new technologies that are really, really helpful to try to understand this idea behind developing an appropriate design storm. One of them is radar. National Weather Service NexRad radars are ubiquitous around the country. We see them 12 times a day on television, on the Weather Channel, on our local news. But they're wonderful devices for figuring out what happened in between the gauges. And they provide the kind of information that we need to actually begin to understand the geometric properties of storms. We now have about 25 years of data that has accumulated since the initial deployment of the NexRad radar system. And we can actually look at individual storm cells at 15-minute time steps, let's say, throughout the entire United States. That gives us access to hundreds of thousands, if not millions, of storm cells to evaluate. In this particular example, we've identified storm cells. We fit an ellipse to that cell. Once we fit the ellipse, we know the area of the cell. We know its aspect ratio, in other words, the ratio between the width, or the short axis and the long axis of the ellipse. We know its orientation, in other words, azimuth from north. We know the peak rainfall within the ellipse, and we know the distribution of rain within the ellipse itself. By looking at these identified cells from time step to time step, we can also assign a speed and a direction. So we end up with a velocity vector. And with that, we can put it all together and we can come up with an idealized shape, which is the result of actual observations from hundreds of thousands, if not millions, of storm cells, depending on the size of your study area and the length of time that you study. Now, with hundreds of thousands of cells to look at, we can actually categorize them by the peak intensity. So you can see a full range of intensities on the right-hand side of our chart, all the way from a couple of tenths of an inch per hour all the way up to 8 inches per hour. One way to actually compare all of those shapes, because each one of those peak intensities is associated with a shape that can be defined by its physical dimensions. But it's hard to actually compare them all directly, so we've done a simplified version of that by normalizing the size of the cells from 0 to 100% and normalizing the peak intensity from 0 to 100%. And then we can cram everything onto one chart and make some assessments. So here we have a set of curves. Each curve is associated with one of the intensities listed in the column on the right-hand side of the chart. In the upper right of that set of curves, those are the lower intensity ones. The higher intensity ones are toward the lower left. So you can see in our list of rainfall intensities, there's a lot of them that are pretty small. As a designer, I'm actually most interested in the more extremes. So let's arbitrarily say I want to get rid of all of the rainfall intensities that are lower than about the 2-year storm. So let's do that. And this is what's left. So those curves represent the characteristic shape for all the storms that we looked at in each one of these intensity categories, all the way from the 2-year event up to the 100-year and beyond. That's actually pretty remarkable. It's essentially the same curve. There's very little variability. I mean, you could do statistical noise and get that kind of variability. But it fundamentally suggests that storm cells at the 15-minute time step have the same characteristic shape all the way from the 2-year event all the way to the 100-year event. That's information we can actually do something with. Now, if I'm really, it looks like it's sort of an extremely exaggerated peak intensity in our little idealized cell shape there in the upper right of our chart. I call it a witch's hat. Let's say I'm interested in finding out the typical area that's under the central, the highest peak intensity of the storm itself. In other words, the tip underneath the tip of that cone. Well, let's arbitrarily pick the 50% level. If we go over and draw a line about halfway up our peak intensity on our idealized cell shape, and then project down to the ground, and that's the area that would be under the highest 50% intensity of our design of our storm cell. Back to our curves, we can see that just 5% of the total cell area is located under the highest 50% of the intensity, peak intensity for that cell. That's another important insight, because when I first saw this, I realized that these peak intensities on a 15-minute by 15-minute basis were actually covering a much smaller piece of real estate than I thought was possible or thought was reasonable. But we've seen this in a number of places around the country where we've looked at storms in this way. The implication from a design perspective is that if the storms are truly focused on a much smaller piece of real estate from time step to time step, that means that most of the watershed is likely not engaged with the high intensities 15-minute by 15 minutes. So if we basically make an assumption that we're going to spread the rain out over a large area, the entire watershed, we're probably going to be overestimating the amount of runoff that's going to occur, because we're simply going to be putting too much water into the watershed. Now, with this additional radar data, how does that impact our development of depth area curves, or how do they, like a radar-based depth area reduction curve, compare to the historical procedures? Well, let's take a look at the hourly curve. Here we have the hourly curve represented by itself, the National Weather Service TP29 curve. They're in the blue at the top for the 1 hour time period. The three below represent the depth area reduction curves that were derived from the radar data. And the first thing you can see, they're a lot lower than the National Weather Service approach. That means that the central intensities, or the point estimates, are decayed in reality much faster than the approach that was behind the development of TP29. The other thing that kind of jumps out is that we get different curves for different frequencies. In other words, different intensities, different size of the storm. That's another important thing that's jumping out at us. Just as a double check to see if this was reasonable, we have an independent study that was basically a master's thesis done by Vince Geronimo in 2004 from the University of Colorado at Denver. And he actually manually sat down and computed the depth area reduction factors using the radar available at the time for 6 storms as the basis of his thesis. And those depth area reduction factors for the individual storms are shown in the dashed lines on the graph. The solid lines with the markers are the same ones that I showed in the previous slide. And Vince's curves kind of cover the spectrum of what he had, but he looked at six storms, and we looked at over 250,000 for this particular event. And I'm pretty satisfied that the radar-derived curves were right in the middle of what Vince had in the Denver area. Now, with this huge database of storm cells that we have, we can actually start accumulating a lot of geometric information about these storms. Again, the size, their shape, the distribution within these ellipses, their velocities, which direction they're going, how do they vary seasonally, how do they vary geographically. We can put all that information together. It actually starts forming the foundation for, rather than a static design storm, actually we have the tools now to develop a dynamic design storm. And we can do that with some clever computer programming, and we can use the geometries that were derived from our statistical analysis of the storm cell sizes and shapes, and tell the computer to run the design storm across a watershed, and we can test sensitivities of how the system responds to a dynamically moving storm. As I mentioned earlier, a key element of these design storms is that they tend to be derived, at least the footprint of design storms tends to be derived at the storm total level. And that can be problematic. And if you can just kind of visualize for a minute that if you are creating isohydal maps or isohydal lines based on rainfall observations, they're typically elongated along the direction of cell travel. So let's make it simple. Let's say we have a storm that's moving east to west. Make the geometry simple. We've got a thin line of thunderstorms that are traveling east to west. And at the end of the storm, you're going to look at the data, and you'll see that the isohydal lines are going to be elongated in the east-west direction. However, if it's a narrow line of thunderstorms oriented due north-south, then only a fraction of that storm total area, only a fraction of that footprint is ever engaged by the watershed in any given time. And if we use the footprint for a storm total and apply that to the watershed, that's another way that we tend to put too much water into the watersheds and overestimate the amount of water coming out for design purposes. And that can be a very expensive proposition. So if you're wondering how well that idea worked, as I was when we first kind of came up with it, let's take another look at this nested design storm that we showed a couple of minutes ago and see how if we can actually reproduce that. Here's the result. So the blue is exactly the same ordinance that we showed in the previous slide. That's our standard nested design storm distribution over a 24-hour period. And the result from our dynamic design storm, by passing this storm over a target location, this is the result that we got. It's very, very close. Now, I didn't get that on the first pass. It was right out of the box. It actually did a pretty good job, but it was a little taller and skinnier than the design storm was. So we changed we changed the speed a little bit. We changed the orientation of the storm cell as it moved across the watershed. It got a little bit better. And what we're seeing here is actually the result of simply the third attempt, just the third attempt of tweaking the parameters slightly. And we virtually identically reproduced the design storm. And you can see in the little table insert, the 10-year frequency from the standard design storm is in the middle column on the right, is the design storm that was created, or the amounts that were created from the dynamic storm processor. So that's really promising. I mean, it does a couple of things. One, kind of suggests that this idea of at least the distribution that is being used for standard design storms is not a bad one. And it's also interesting that we could actually replicate that using an entirely independent approach, using our understanding of the geometric properties of storm cells and how fast they moved across an area. So how does seasonality affect some of these curves? Well, again, I've reproduced the National Weather Service TP29 curve. This one now is for the 15-minute time step. And you can see up to about 50 square miles or so in watershed size. They all roughly mimic what the National Weather Service curve is. But once you get on beyond about 50 or 60 square miles, the Weather Service curve levels off, and the actual radar-based curves still continue to decay. And it's more indicative of the actual storm event. We also noted that this pass was, we go back and we can see that now we're looking at a winter month, and we get a different look at these storms. And so we see the element of seasonality kind of sneaking into the picture. It's something else that we have to consider. Now, most of the work that we've seen so far is limited to about a 400 square mile area. The Oak Ridge National Laboratory a couple of years ago set out to use the PRISM data set, which is a topographically influenced gridded data set over the entire country. And they decided, so, well, we're going to use that data set and see what kind of aerial reduction factors they can derive and see if they vary across the country. And in fact, they do, and they do quite a bit. Also varies by location around the country, because you can see not only do they vary locationally, but you can see that California is a lot different than Texas, and Florida is a lot different than Washington, and so on. Now, this particular one, I'm not sure how valuable the exercise is, because I'm not sure I understand what the actual rationale would be to have an average rainfall from a point value over 1,000,000 square mile area. But nonetheless, it was an interesting exercise to see what the variability is. Looking at the same data in a slightly different way, here we have a map of the United States, and you can kind of see some of the regional differences. The rows represent 400 square mile, 2,000 square mile, and 10,000 square mile watershed sizes. The columns represent different frequencies, from the annual maximum series to the 10-year to the 100-year. So you can see in general, there is a greater and greater reduction as you increase the watershed size, and a greater reduction as you increase the peak point rainfall amounts. And interestingly enough, Texas has the most severe reduction for the largest areas. So what have we learned? Well, we've basically learned that using some of this newer technology, in particular radar-based approaches, we definitely see that there's a seasonal variation. We see regional variation and variations among these depth area reduction factors by frequency. We see impacts of storm type. Is this a hurricane? Is this a frontal system? Is this a standard gully washer in central Texas dominated by heavy convective activity? There are differences in the precipitation products used. There are different philosophies to calculate the DARF in the first place. How do you address the issue where the storm size is much smaller than the watershed size, for example? You have watershed shape as a major factor. Some places in the country you have kind of short, fat watersheds, but in Texas you've got a lot of long, skinny ones coming out of central and west Texas and heading to the Gulf. Those probably need a different approach to the design storms. And oh, by the way, this I'm sitting here making this recording in California when it's 105 degrees outside. This climate change stuff is a real thing. So I want to talk briefly about a couple of new statewide studies that are just underway. One is in Texas and one is in Arizona. In Texas, the Corps of Engineers has basically contracted with West Consultants. The Corps of Engineers is coordinated, at least this effort is coordinated by Jerry Cotter out of the Fort Worth district and aided by Simeon Benson. West is the prime contractor, and we are collaborating with 3 universities in Texas, Nick Fang from University of Texas at Arlington, John Nielsen Gammon, state climatologist and professor at Texas A&M, is leading their team, and then Dr. Phil Bedient from Rice University is leading that team. And oh, by the way, nice shout out for Dr. Phil, Dr. Bedient. He was just recently named the recipient of the Ray Lindsley Award from the American Institute of Hydrology. It's one of their highest awards given to exemplary service throughout an illustrious career. And so congratulations, Dr. Bedient. The Arizona study is co-funded by the Flood Control District of Maricopa County and the Arizona Department of Transportation. West is also the prime contractor with Applied Weather Associates as one of our principal subs. And here's the objective of the storm study in Texas. Now, important thing to note here, one of the things that we're concentrating on is actually the larger basins. Again, this is the funding is coming through the Corps of Engineers. They are very interested in how to approach, especially in Texas with the complexity of storm systems you have there, how to deal with design storms over these larger basins. What's that going to look like? And again, with the idea of if we put a 100-year storm in, we'd like to see a 100-year design flow coming out. And if we can't, we need to understand why and how to deal with that issue. So some of the key points of the Texas storm study is to identify homogeneous regions around the state where we can apply a common approach. So we may have one approach out in West Texas, a different approach in the Piney Wood section of East Texas, for example, and maybe a third or fourth or fifth, depending on where you are in the state. In each one of these regional approaches, we want to consider storm type, its climatology, the meteorology, topography, coastal influence, geographic extent, and anything else we can think of as we're wading through this project. In terms of schedule, we just started and we're due to issue a final report in 2023. So we have a little time left for that. But it's a really exciting opportunity to use some of the latest technology to get a really good handle on what storms actually look like and then have that represented in design processes that accurately reflect the complexity of storms in the state of Texas. So we've come a long way. We now have a lot more data than we had in the 1950s. Not only a lot more rain gauge data, but we have new technology like radar data, high resolution data. So instead of worrying about a rain gauge every 50 or 100 square miles, we worry about rainfall observations that have a resolution on the order of 50 acres. Big difference. We also have some wonderful automated tools and geographical information system tools that we can use to actually analyze these large data sets in an effective way and do it efficiently. And we can also test some of the simplifying assumptions that were made 60 or 70 years ago and see if they're still valid today. So this is an exciting opportunity, exciting position that we have in our profession. These changes that are going to be made as a result of new design methods will literally impact billions of dollars of constructed water infrastructure. Thank you for watching today. Appreciate your time. If you want any more information or have questions, my email address is there along with my colleagues Ramesh Shintala in our Dallas office, and his email is there as well. Feel free to contact us at any time. Thank you.